So no, there's no questions about your homework probably.
Okay, we are going to talk about, we've been talking about Pythagoras. Let's actually talk about Pythagorean theorem today. I feel like in geometry, we did not, there it is, spend much time on Pythagorean, as much time as I wanted to on Pythagorean theorem, so we are going to take some time on it today. Okay, so let's talk about Pythagorean theorem. So Pythagorean theorem is a squared plus b squared equals c squared, specifically with a right triangle. And with your right triangle, C is your hypotenuse, and then A and B are just the lengths of your legs. They can be flipped. It doesn't matter which one's A, which one's B. But C is the one that matters, and that's the relationship. So Pythagoras gets credit for the Pythagorean theorem, hence his name. But we have a Babylonian clay tablet, the Plimpton 322 Babylonian clay tablet from 1800, about 1800 BC. And there are Pythagorean triples on there. So what are Pythagorean triples? Pythagorean triples are numbers that work in this, right? So there's a couple of really common ones. Do you know what one of them is? Three, four, five is one that works. 3 squared plus 4 squared equals 5 squared, because 9 plus 16 equals 25. So 3, 4, 5 is a Pythagorean triple. There are other ones at the end of class, or maybe on Thursday. We'll see how far we get today. We will have a couple of ways to come up with some more of those. So we have proof of sets of these numbers that work in this relationship well before Pythagoras. So it is pretty obvious that he wasn't the original founder of Pythagorean theorem. Okay. Pythagorean theorem is one of the most well-known theorems. I'm going to make the statement. I don't actually know how true it is, but I think it's one of the most, like, has the most proofs for it. Okay, so there are over 300 proofs for Pythagorean theorem by different people, like some of the famous people that you might know. One is a mathematician, Euclid. Okay, also Leonardo da Vinci did a proof. So he's not like a famous mathematician, he's a famous person. And then we had a President James Garfield actually has a proof as well for Pythagorean theorem. Okay, so today we are going to go through 3 proofs for Pythagorean theorem. One of them is going to be the President's proof. And then we have Bhaskara's proof, and then one using symmetral triangles. So we're going to go through 3 of them today. And then in your homework, I have linked, let me go ahead and pull that up. So your homework that I'm assigning today, oh, you can't see this, let me switch over. So your homework for today has some stuff from the triangular numbers and the square numbers, but right here, number 7, it says go to this website. And when you, okay, fine, let me copy and paste it. Come on. When you go to this website, sorry. It has a ton of proofs, like here's number 1, number 2, number 3, and it shows all these different proofs of Pythagorean theorem. I mean, let's see how many total there are. There are 122 proofs, different proofs of Pythagorean theorem. So you are going to pick one of them that makes sense to you, and you're going to do on your homework. Okay, so if the first one doesn't make sense, move on to the second one, move on to the third one. Some of them are like this one's obviously a lot of pre-cal, like maybe you don't want to do that one. But there are lots of different proofs with lots of different things. So we're going to do 3 of them today, and obviously these 3 are off limits since I'm doing these. The first one we're going to do is Bhaskara's proof. Let me go ahead and start on the issue paper. It doesn't take more than half a page. I just want to make sure I have room. So Bhaskara's proof. Okay, so for Bhaskara's proof, we are going to start off with a square. So draw a square. And in our square, we're going to have a length of C. So all sides have a length of C. And within that square, we are going to put in some right triangles that look like this. So let me draw 2 of them and you'll kind of see the pattern. So the first one's kind of weird drawing it in, but it's because I need this one to be the tip like that. That. And then this is going to be like that. And then this one's going to go, oh, something like that. And all 4 of those triangles, we're going to call them right triangles. So we're going to say this is a right angle, this is a right angle, this is a right angle, this is a right angle. So I've got a bunch of different shapes here. I have the big square on the outside. And within the big square on the outside, I have 4 right triangles. And then what is the shape on the inside right here going to be? A square also, specifically because I have 4 right angles right there, right? So let's label some measurements. We're going to call this measurement over here A. Let me make sure. Yep. This small measurement right here on the small side is going to be A, and the longer side is going to be B. So I have some different things. I have a big square. I have a right triangle, which I actually have 4 of them, right? And then I have a small square. Okay, so let's talk about the areas of each. The area of the big square. How do you find the area of a square? Area. Length times width. So for the big square, what's it gonna be? C times C, which is C squared. Agree? Okay, the right triangle is going to be 1/2 base times height, or base times height divided by 2, right? So in this case, the base is B, the height is A divided by 2, because I don't know this height, so I don't want to use C as my base. So like turn it and use B as your base and A as your height, right? So it's going to be A times B divided by 2. Length times width divided by 2. Or 1/2 base times height. The small square, this is the one that gets a little bit harder. So looking at the small square, what is this length right here? It's not B, B is the whole entire thing. It's B minus, what's this length right here? If you turn it and look at that triangle, that's A right there.
Oh,
So, and this is B up here. This is A right here. This is B up here, right? All the way around. So this length right here is the whole length of B minus A. Okay, so this would be B minus A. Would be that length. And it's a square. So they're all B minus A, right? So the area of the small square would be B minus A squared. Okay, so I have these formulas for the areas here. Do I have a relationship with all the areas? What would you say? Couldn't you say the big square area is 4 of the triangles plus the small? Couldn't you say this equals this plus this, or 4 of those plus that, right? So let's write it. The area of the big square. So like the ideas I'm doing. Area of big square equals 4 times area of the triangles plus area of the small square. Oops, sorry. So I'm going to plug in my formula. C squared equals 4 times A times B divided by 2 plus B minus A squared. At this point, this is just algebra. Let's go ahead and simplify it. C squared equals 4 times A times B divided by 2 would be 2AB. 4 divided by 2 is 2. And then B minus A squared, let me multiply that out. B minus A times B minus A. When I distribute it out, I get B squared minus AB minus AB plus A squared. What happens with 2AB minus AB minus AB? Cancels out. Left with C squared equals A squared plus B squared. And since I labeled my measurement of A as a side length of a right triangle, and B as a side length of a right triangle, and C as the hypotenuse of a right triangle, then there's your Pythagorean theorem. So that's one proof. We're going to do another proof. This is President Garfield's proof. Okay, so this is President Garfield's proof. Okay, so we are going to start with 3 right triangles. 2 of these right triangles are going to be congruent. 2 are congruent. And the third right triangle is an isosceles right triangle. So we're going to draw one of our right triangles like this. So we're going to say this is A, this is B. We're going to draw the other one like laying down on its side. So we're going to draw it like this. So the B is the long, the A is the short. From here, if my third length is my hypotenuse, if this is C and this is C, that actually fits perfectly an isosceles right triangle, because this leg is congruent to this leg, so it's isosceles. How do I know it's a right triangle? How do I know that it is? This is a right angle. How do I know that's a right angle though? The idea is 3 legs have, I'm sorry, 3 angles have to add up to what? 180. So since this is 90, these 2 have to add to be 90, right? So call this X, this is 90. Right, pardon me, 90 minus X. Agree? So same thing over here, the one across from A would be the X. And 90 minus X plus X is 90, and it has to be 180. Right? Like these 2 add to be 90. So that has to be 90 no matter what. Okay. So I have my 3 triangles that we talked about here. I have these 2 that are congruent. And then this is my third isosceles right triangle. Okay. So we're gonna do the area thing again. What's the area of the big shape? Or what's the shape? What is the big shape here? This is different than this.
Oh.
A trapezoid is actually a right trapezoid. Okay. So this is the big thing is a trapezoid. What's the formula for area of a trapezoid? Do you remember? You add the 2 bases, base 1 plus base 2 times height divided by 2, or 1/2 times height times base 1 base plus base 2. So the big shape is the trapezoid, and then I have 3 different triangles inside, right? So I have 2 of the congruent triangles, 2 of the congruent triangles. The formula for those would be 1/2 base times height. And then I have the isosceles triangle. Isosceles, I have a hard time spelling that one. Is again 1/2 base times height. So for my two congruent triangles. My base is A and my height is B, or vice versa, B and A. So the formula here would be A times B divided by 2. How about for your isosceles triangle? What's for this one in the middle? What's the base and what's the height? C and C. So this is going to be C squared divided by 2. And then this one, the base 1 plus base 2 times height divided by 2. Your base 1 and base 2 are the ones that are parallel. So it's not, this isn't base, this is base, this isn't base. It's actually, that's the base and that's the base, right? So base 1 would be B, base 2 would be A. What's your height? A plus B. So the formula here for this one, I'm gonna write it. This is B, this is A, and your height is A plus B. So the relationship again, area of the trapezoid equals 2 times area of the triangles. Goodness. Triangles plus the area of the isosceles triangle. So your trapezoid area is B plus A times A plus B divided by 2 equals 2 times the area of the triangle is A times B divided by 2 plus the last one is C squared divided by 2. Let's simplify it. What do you want to do first? Just algebra at this point.
2 times the first one.
2 and 2 cancel out? Sure.
The other one?
There's not 2 multiplied over here.
No,
Oh, it's only 2 times this one, not times that one.
I know, but the squared.
I'm gonna go ahead and multiply this out. B times A, B plus A times A plus B. B times A is BA. B times B is B squared. A times A is A squared. A times B is AB, or I'm right, is BA. Divided by 2 equals A times B plus B squared divided by 2. What's next? Do you like the fractions? How do you get rid of them? You just multiply by the denominator? Like, multiply everything times 2? So I gotta multiply everything on this side of the parentheses times 2. I have to multiply everything on this side of the parentheses times 2 also. So those cancel out, right? These cancel out, but I also still have to multiply, like distribute it. I still have to multiply this times 2. So I end up with over here on the right hand side, 2AB plus C squared. On the left hand side, I got B squared plus A squared plus BA times plus BA would be 2BA or 2AB. Put these two together. And then subtract off the 2AB. And what are you left with? A squared plus B squared equals C squared. And A was the side length of a right triangle, B was the side length of a right triangle, C was the hypotenuse of a right triangle. So Pythagorean theorem proved again. Okay, we're gonna do one more proof. This one is using similar triangles this time instead of using area. So this is called the similarity proof. So we're gonna start with a right triangle. We're gonna call it ABC. So the right angle is going to be up here. This is angle A, this is angle B, this is angle C. Which makes, did I do it right? Nope, I did it wrong. This is going to be B down here, sorry. This one's going to be C up here. So that C, the little c and little a across and little b across. So C ends up being the hypotenuse. Side C is across from angle C, side A is across from angle A, side B is across from angle B. Okay, let's construct a perpendicular passing through C and intersecting AB at a new point, let's call it D. I'm going to draw that right there. And this is perpendicular line. And this is my new point right here is called D. Okay, so now I have two right triangles within my big right triangle. Agree? Okay, so I have triangle ABC. That was my original right triangle. I have this new one, ACD, triangle ACD. That's also a right triangle. And then I also have CBD, triangle CBD. So we went over proving triangles are congruent. Here I do not have congruent triangles, right? I have what we call similar triangles, and we didn't really go over how to prove similar triangles, but one way of proving similar triangles is if you have two angles that are congruent, then the triangles are similar. Because if you have two angles that are congruent, that means you're going to have three angles that are congruent, because the third one will be also congruent. And then the triangles are similar, same shape, different sides. So looking at the big one, ABC, and ACD, this little one right here. Do you see two angles that are congruent? What's one of them?
the,
The the right angle, right? So there's a 90-degree angle there and there's a 90-degree angle up there. So check these two both have a 90-degree angle in common. Not in common. They both have a 90-degree angle. It's two different ones, but they both have 90 degrees. Do they have an angle in common? I'm talking about the big one and this one right here.
two. No, I have one A.
This one, angle A, is the same on both of them, right? For the big one, it's CAB. For the little one, it's CAD, right? So those are congruent because it's the same angle. So they both have a 90-degree angle, and then they both have angle A. So that means that these two are similar to each other. Same shape, different size. Same thing with these two over here. The big one, A, oh, actually, not the big one. Huh? If I do the big one to the other small one, it's the same idea, right? The big one to the other small one, both have a 90-degree angle, and then they both have angle B in common. Agree? So it's like this one's similar to this one, but this one's similar to this one. So therefore, those are similar also. All three of these are similar. Okay. Okay, so all three of those triangles, and there are all similar triangles. Once you have similar triangles, then you know that the ratio of the sides are equal, right? We do this all the time. The idea, if I, like we did it with the shadow, right? If I have some pyramid, right, and it's casting the shadow that's this long, so I know if I'm this tall and I'm casting a shadow that's this long, here's my triangles, right? Like the height, this is congruent, or this over this equals this over this. Yes, this is A, this is, let's call it big A, this is little a, this is big B, this is little b. We know that big A over little a equals big B over little b because they're similar triangles. Okay, so same idea here. I can do the same thing if I had C, so let's think through. CB, this one right here, CB. Is to DB, is to that one, as AB is to CB. Let's see. So these are both the tops. CB and AB are both a hypotenuse, right? AB is the hypotenuse of the big triangle. CB is the hypotenuse of this one over here. And then down here, CB is this leg, DB is that leg. So I have that ratio. The other ratio you have using the little triangle and the big triangle is the hypotenuse AC on top of the little one. The big triangle would be AB. And then the short side here would be AD. The short side for that one would be AC. So these are just the ratios of the legs. And then let's put in letters where I have them. CB is the measurement of A. Oops, sorry. This distance CB is the measurement of A. So I can replace that with an A on top. Same thing with an A on bottom because those are both CB. AB also has a measurement. What's the measurement of AB? C. And then same thing, C is the measurement of B up here. I don't know AD. AB up here is C. And AC is the measurement B. And then let's go ahead and like cross multiply right here. A times A is A squared equals C times DB. I'm just gonna write it as C times DB. Same thing over here. B squared equals C times AD. And then from there, let's add these equations together. On the left-hand side, I would get A squared plus B squared. On the right-hand side, I would get C times DB plus C times AD. I can factor out a C there. There's a greatest common factor of C. If I factor out a C, it would be DB plus AD, right? I pulled the C out and distributed the C. And then DB plus AD, look at that. DB plus AD. What's D? I'm sorry, you can't see. What is DB plus AD? AB, which is C. So this becomes C times C, which is C squared. So A squared plus B squared equals C squared. That was long. That was a lot. But 3 different ways of proving right there. There are over, we said 300 proofs. Yeah, over 300 proofs. So you're going to find one more that makes sense to you. I don't care which one. Pick one from the list, one that actually kind of makes sense, and you're going to do that in your homework. So, that is extensive proof on Pythagorean theorem. But one of the problems with the actual Pythagoreans with this theorem is it actually caused a lot of distress to them. So Pythagorean theorem caused a lot of distress to the Pythagoreans because it works with irrational numbers. And generally, unless you have a Pythagorean theorem, no, a Pythagorean triple, most of our numbers are irrational numbers with the Pythagorean theorem. And when you look at the most basic version of it, let's do a right isosceles triangle. Oops. If I want it to be isosceles, then these 2 legs have to be congruent. What's the easiest number to assign to those 2 legs? 1, the 2 congruent legs. You put a 1 there and a 1 there, right? I think that's your most simple version of the problem. What would this over here be? 1 squared plus 1 squared equals C squared. So C squared equals 2. So what is C? Take the square root, right? The square root of 2. That gives you the length of the square root of 2, which is not a rational number. And remember that the Pythagoreans, the big thing for them was everything was based on rational numbers. We wrote that. Let's see if I can pull up those notes. We wrote, where's that? That they wanted everything to be a ratio of integers. So something that could be written as a fraction. And this is the problem. You can't write square root of 2 as a fraction. That's like literally the definition of an irrational number is can't be written as a fraction. So this kind of rocked their world. And I think in the video, didn't it have that talk about Hypatus or Hypatus or whatever, and they like drowned him basically. Like there's a story that they drowned him because it's like this showed that everything you like base your mathematical work or your cult following or whatever, everything they based it on was no longer true. So it's like if your whole world is built on this basis of irrational numbers don't exist, and then they do exist, like it all falls apart at that point. So that kind of goes to show that this is why math is built on a rigid set of basic assumptions. And we talked about this a lot last semester in geometry, because in geometry, everything was built off of our basic assumptions of our building blocks, point, line, and plane. And then we had theorems that we created from it, and then postulates and axioms and all those sorts of things. So it's like you have to have the foundation being correct to be able to build on top of it, or else it's all just going to fall apart at some point. This also kind of shows why. So another thing that we talked about, like on one of the first days of class, I think I actually put it on my iPad. Let's see. I think I did put it on my iPad. Remember we talked about like the order of things, of numbers? Yeah, it's on the other one. We talked about the first numbers were our whole numbers. What was after whole numbers? You remember, it's like the first day of class, the very beginning. Weren't irrational numbers next? I said whole numbers. Oh, fractions, yes. We already talked about fractions. And then after fractions, irrational numbers. So that's where we're at now. So it seems like when we teach math, we talk about like negative numbers before irrational numbers, but it's like this is the discovery of a situation where irrational numbers came up first, and then after irrational, what's next?
Negative.
That's still a while away. We still have a little while before you get to negative numbers. So that's the reason why this came first before that, because it just kind of worked out with the things that they were dealing with, that irrational numbers popped up. So the interesting thing about the Pythagoreans is they kept this a secret. So they actually are the first people to discover irrational numbers, but it's not necessarily credited to them because it would have ruined everything they stood for. So they kept it a huge secret, and people did not use irrational numbers for a while longer. But there is actually a way to generate Pythagorean triples. So remember what Pythagorean triples are? Like 3, 4, 5, the numbers that you can plug into Pythagorean theorem, using triangular numbers. Okay, so let's do a few of those. Pythagorean triples using triangular numbers. So the idea is, I'm gonna write the equation first, and then we'll talk about what A, B, and C are. 2n plus 1 squared plus 4 times the triangular number, or the nth triangular number squared, equals 4 times the nth triangular number plus 1 squared. The nth triangular number. So whatever you pick for n, it's going to be t sub 1, t sub 2, t like the triangular number. So the idea here is this is A, this is B, this is C, right? Because A squared plus B squared equals C squared. So to come up with one of the triples, you pick a number for n. So let's start off with n equals 1. So if n equals 1, A would be 2 times 1 plus 1. which is 3. B is 4 times T sub n in this case is 1. So this means 4 times the first triangular number. What's the first triangular number? What we did last time? The first triangular number is just 1 dot, 1. Okay, so this would be 4 times 1, which is just 4. And then our C value would be 4 times the first triangular number plus 1, which would be 4 times 1 plus 1, which would be 5. So the Pythagorean triple would be 3, 4, 5. Like we already knew that one, but that's kind of like using the formula to get it. Do another one. If I wanted to generate another set of Pythagorean triples, I would pick another value for n other than 1. What do you want it to be this time? Oh, you're gonna have to find the 6th triangular number to be able to do that.
Oh,
Let's do 2. So it would A would be no. Let's do it. Let's do it. Why am I discouraging this? Okay, so n is 6. So A would be 2 times 6 plus 1. 2 times 6 is 12. 12 plus 1 is 13. So that's the first number in your triple. B is going to be 4 times the 6th triangular number. How do I figure out the 6th triangular number? I could look at the pattern, or remember I have formulas. We wrote our formulas down. To get the 6th triangular number, I do 6 divided by 2 times 6 plus 1. So 6 divided by 2 would be 3. 6 plus 1 is 7. 3 times 7 would be 21. 3 times 7?
oh, yeah.
21. So the 6th triangular number should be 21. So 4 times 21. And 4 times 21 is what? Let's see, 84. And then the third, or C, would be 4 times the 6th triangular number plus 1. So 4 times 21 plus 1, which would be 85. So 13, 84, 85 is also a Pythagorean triple, apparently. Who knew? We could check it. How could you check it? Is 13 squared plus 84 squared equal to 85 squared? Let's see. 84 squared. 13 squared is 169. 84 squared is 7056. And 7056 plus 169. When I take the square root, I get 85. Looky there. Good job. So this 13, 84, 85 is a Pythagorean triple. Okay. Let's go ahead and we're gonna finish it up. Okay. So the two things we're gonna finish with is we're gonna talk about why is Pythagorean theorem so important. Okay. So this is the importance of Pythagorean theorem. Huh? Oh. Okay, one reason why it is so important is because it is, or we cover it so much is because it is algebra and geometry. Okay, so it's an algebraic formula that is connected with a geometric idea. So it's a connection between algebra and geometry. one reason is like the most famous of the theorems. I would say anybody, if you ask, say one theorem from math, they would say Pythagorean theorem, is because it's actually useful. It's useful in finding distances. It's actually also has a connection between distance and area. So the picture of Pythagorean theorem is, right, the triangle. If this is A and this is B and this is C, the picture of it, A squared, is going to be a square that has a length of A, right? So whatever the length of A is, let's draw it out. Let's actually draw a square like that. Like this square has a area of A squared. Same thing with B. This square, if I go length B this way, has an area of B squared. And then same thing here, if I go out C this way and draw what doesn't look like a rectangle, it's supposed to be a square. That has an area of C squared. So the picture here is this area plus this area add up to be all of that area. And we're specifically talking about the distance from A is from this dot to this dot, and B is from this dot to this dot, and C is from this dot to this dot. The next thing, it is directly responsible for the discovery of irrational numbers. And then also, it's a generalization that can be applied in different situations. So I'll show you some. So a generalization that can be applied in other situations. There we go, goodness. Okay. So some situations, you can actually, this picture was with squares. You can actually do this picture with semicircles. So instead of it being a square, it being a semicircle here that we're talking about, your area. So a semicircle all the way like that, and then all the way like that. You can do it with parallelograms. You can do it isosceles triangles. So like you can apply that a lot of different ways geometrically. Also in pre-cal, your law of cosines is Pythagorean theorem. Do you remember the law of cosines? Was it c squared equals a squared plus b squared minus 2ab cosine c, right? And the specific version of this is when c is 90 degrees, cosine of 90 is 0. Cosine of 90 would be up. Yes, would be cosine of 90 is 0. And 0 times that is 0. So you're just left with that. So law of cosines is essentially, this is Pythagorean theorem for non-right triangles. The Pythagorean theorem is only for right triangles. Law of cosines is Pythagorean theorem for things that are not right triangles. Okay, so that's where we're going to stop. You should be able to do all of week 4 homework based on this, because it's all stuff we did last week, the triangular numbers, square numbers, and then Pythagorean theorem and the triples. And then we're going to move on to the next bit of information on Thursday. So you have your birthday project coming up that's due. And then this is going to be due next Tuesday night at midnight.